So we'll just call this a calc 2 extension. I don't know what else to call it, so that sounds good. Methods of proof. So just to kind of preface this, proof really is the essence of math. So solving problems with formulas and equations and that kind of thing is really, well, initially, all those formulas and equations have to be, in order to be accepted, they have to be proven. They have to be shown to be valid. Mathematics, kind of told the joke on Friday about mathematicians don't accept anything until it's proven. That's kind of how it is with all of these formulas, that eventually we try to prove that they're valid. So Newton, Leibniz came up with calculus, and eventually people went back and said, okay, here's what makes all of this stuff mathematically valid. And using formulas and equations to solve problems like we're doing is really more kind of in the realm of applied mathematics or science or engineering. And the math that we do in school is really the math that's kind of preparing you for science, engineering, that kind of thing. When you go past using math to solve problems and more to kind of the logical foundations of math, then you get to this idea of having to prove things. Like I said, I just want you to have at least some exposure to these methods so that if you see them in a class, if you choose to take a double major, or if you choose to take a class beyond differential equations, for example, if you take an analysis class or modern algebra class or something like that, and you're asked to prove things, you'll have at least some idea of what the instructor is talking about when you go about these things. So the first one that we're going to talk about, it's not in the handout that I gave you, is direct proof. And that's the one that we probably have the most familiarity with. So direct proof is like most of the proofs that you did when if you had to do proofs in geometry, if you had to write a proof in geometry, prove that two triangles are congruent. Well, you know that this is true, and then you know this is true, this is true, this is true, so this has to be true. So that's a direct proof. The most basic example that we would use, and sometimes that's all that's involved in a proof, is using a formula to establish a result. So for an example, a direct proof that we might do, that we might see in the context of calculus, is a very simple example. Show that the area under f of x equals x squared from x equals 1 to x equals 0 to x equals 1 is 1/3 square units. So that's just a really easy example. What would we do to show that this is true? Integrate. So we would say the area equals the integral from 0 to 1 of x squared dx, which equals 1/3. We're accepting that the integral gives us the area under the curve. We don't need to prove that. So we know that if we integrate, that we get 1/3. And we do some homework problems where it will say show that this is true, or show that the volume of this surface solid of revolution is such and such. We had one. No, the one we did the other day was just to find the centroid. But we will see problems that say show that some property of this thing is such and such, and you're just using your formula to come up with the answer. So that's the most basic kind of direct proof. More interesting examples start from, and most of mathematics starts from, definitions. We define things, and we have some axioms, some things that we're assuming to be true. So let's talk about a couple of those. So starting from definitions and axioms. So definitions are just like they sound. Axioms are things that we're assuming to be true. So let's talk about an even integer. Let's come up with a definition for an even integer. What do we mean when we say an integer is even? No remainder when we divide by 2. And another way that we could say that, instead of talking about division, we could say that it is a multiple of 2. So to make that more formal, we're going to say an integer is even. And we could say positive integers if we wanted. Integer is even when, this is how you'll see it in like a fancier math book, when it can be expressed as 2n, where n is an integer. And what do we mean by an integer, just so we make sure we're all on the same page? Like 1, 2, 3, 0, -1, -2, -3. We could limit this to positive. Does it make sense to say -3 is odd? I kind of think it does, yeah. Yes? Zero, we could represent 0 as 2 times 0, right? So it could be even, right? Well, and then when we talk about odd, so now we have an even integer. An integer is even when it can be expressed as 2n, so it's 2 times something. How about an odd integer? How are we going to define an odd integer? 2n plus 1 is 1 more than an even integer, right? Yeah. So.
What about 1?
1 is not even.
My bad.
Right?
My bad.
So, and we could say 2n minus 1 as well, right? 2n minus 1 for an odd integer. I usually like plus. So we're going to say an integer is odd when it can be expressed as 2n plus 1, 1 more, or 2n minus 1, where n is an integer. And then we can do lots of interesting, kind of fun little exercises with these kinds of things. So let's talk about a direct proof. Let me make a proposition. So here's my proposition. My proposition is the sum of 2 odd integers is even. And if we thought about this, does this make sense? 3 plus 5 is 8. 7 plus 9 is 16. So when we try it with some numbers, that makes sense. But we want to show this is true for every single possible combination of odd integers. All right, so any ideas how we're going to do this? Mm-hmm. So we're going to say let 1 be 2n plus 1 for n an integer, and the other be 2k plus 1, where n and k are integers. And then let's add them together. 2n plus 1 plus 2k plus 1 equals, when I add these together, I get 2n plus 2k plus 2. And now what are we going to do to show that this is even? Factor out the 2. This is 2 times n plus k plus 1. N plus k plus 1 is an integer, right? Because when we add integers, we get integers. So we have 2 times an integer. Which is even. And we've established this proposition for every possible pair of odd integers. So that's an example of a direct proof. And one thing that I want to mention about proofs is we need to be careful about assuming things that seem obvious, because sometimes things seem obvious that aren't true. I had a quote up in the back of the room a few weeks ago that said obvious is the most dangerous word in mathematics. Because sometimes things that seem obvious really aren't true, and sometimes things that seem obvious are really difficult to prove that they are true. And it's interesting because when we do our unit on sequences and series, people will claim that such and such is the sum, or that such and such is the expression for the nth term, and it actually takes a lot of work to show that it's true. And it's kind of a fun exercise there, because that's really the closest we get to doing this kind of math is when we talk about sequences and series. All right, questions there? All right, the next one that I want to talk about today, the next method, so that was direct proof. We start with things that we know, and we show that other things have to be true. The next method is, I want to talk about contradiction and counterexample. Proof by contradiction, I really like proof by contradiction. I like when they work that way. But let's start with a counterexample. We can always prove that something is false by supplying one counterexample. You only need one. So when you can find a counterexample, when you can think of a counterexample to a proposition, it's really nice because that's all you have to do is think of the counterexample. Thinking of the counterexample can be difficult. Well, let me make a proposition here. Let me make a claim. If the sum of 2 integers is even, then both integers are even. So that's my proposition. Because 2 plus 2 is 4, 2 plus 4 is 6. So when our sum is even, then both of them have to be even. What do we do to disprove this? Add 2 odds. What am I going to add? 3 and 5. We just talked about it, right? 3 plus 5 equals 8. That disproves that proposition. That's all we have to do. Provide one counterexample. And we just did a direct proof that we actually did the proof in the other direction. We said if both integers are odd, then the sum is even. So we kind of did a proof that this, kind of the opposite way, that this wouldn't be true. So that's one way that I can disprove a statement, is by finding a single counterexample. Now sometimes finding a single counterexample can be difficult, but it's nice. You can save a lot of work if you can think of a counterexample. Now proof by contradiction is a little different. We're not finding a counterexample. what we do with a proof by contradiction is that we assume the opposite of what we want to show. We assume the opposite of what we want to show, and then show that this leads to a contradiction. So if what we assumed leads to a contradiction, then what we assumed has to be false, and the original thing has to be true. In contradiction, I just mean something, a false statement, or something we know is not true. So that means the assumption that we started with has to be false. All right, so let's do, I want to do one example, and this leads us to a really nice example, a really famous example. So I'm going to say if m squared is even, then m must be even. So we're going to assume the opposite of this. We're going to assume m squared is even, but m is odd. And we're going to show that this leads to a contradiction. So we're assuming that m is odd. So if m is odd, how can I write m? Two n plus 1. For n is an integer. So m squared, square this, 2n plus 1 squared. And when we square this, I get 4n squared plus, what do we get, 4n plus 1. And this plus 1 should be a clue here. So I'm going to rewrite this. I'm going to factor out a 2. 2 times 2n squared plus 2n, out of just this first part, plus 1. Well, what is that? This is odd. N squared, 2n squared plus 2n is an integer. So I have 2 times an integer plus 1. Which is odd, but we assumed what? We said that m squared is even, which is a contradiction. So this is a contradiction. So m must be even. So now we have that if m squared is even, then m has to be even. And now we're going to use this for a really nice proof by contradiction. All right, everybody follow there. We assumed that m was even, said m is even, but m squared is even, but m is odd. And we showed that that led to a contradiction because if m is odd, that means m squared has to be odd. Okay. Here is our nice proof by contradiction. Something that we assume all the time, we use all the time. Square root of 2 is irrational. We know this is true, right? We know square root of 2 is irrational. We've talked about square root of 2 being irrational since who knows when. Well, now we can prove it. And this is how Euclid showed that square root of 2 is irrational. first off, let's remember what we mean by a rational number. What's a rational number? As a fraction of two integers. So rational number means we can express it as a fraction of two integers. We're going to do a proof by contradiction. So assume that square root of 2 is rational. So that means square root of 2 can be written as the ratio of two integers, fraction with two integers, where a and b are integers. So I'm going to square this now. So a squared over b squared equals 2. Or 2b squared equals a squared. Well, what does this tell us about a squared? It's bigger than b squared. It's twice b squared. So a squared is, it's 2 times an integer. So a squared is even. So this implies a squared is even. So I'm going to say, and if a squared is even, what does that mean about a? A has to be even. We just showed that that's the case. So let's let a equal 2k for some integer k. So going back up here, I get 2b squared equals 4k squared. Just substituting 2k in here for a. And that says, or b equals 2k squared. B squared equals 2k squared. Well, what does that say about b? B has to be even. So we have a and b are even. What does that say about a and b? They each have a factor of 2. And there was one thing that I forgot to mention up here. We're assuming that this a over b is in lowest terms. Forgot to write that in. A over b is in lowest terms. So we've already reduced this fraction. We can write square root of 2 as a fraction in lowest terms. The lowest terms means that the fraction has no common factors, right? But we just say a and b are even, so they have a common factor of 2. Which is a contradiction, because we said that this is a fraction in lowest terms. So that implies that square root of 2 is irrational. Assuming that square root of 2 is rational leads to a contradiction. Leads to the fact that a and b both have to be even. They have common factors, even when we said that this is a fraction in lowest terms. So a little more subtlety there, but that's a nice proof by contradiction, relatively straightforward. All right, questions there? What's that?
Would you tell us that you have to do 5 proofs when you don't work last night?
Let me think of one that I had to do last week was so we're working with sequences, and there's this idea of with sequences what we call a least upper bound and a greatest lower bound. So a convergent sequence, a bounded sequence has a least upper bound. So there's some upper bound that's the smallest one, and it has a greatest lower bound, some lower bound that's the smallest one. So one that we had to do was show that that the least upper bound of some set A equals minus the greatest lower bound of minus A. And then what is one that there were several about convergent sequences, so you had to use the epsilons a lot. So you're assuming that a convergent sequence show that implies something else. So those were the kinds of things. Last year I had to do a lot of proofs that involved the Fibonacci sequence. So you do kind of manipulating the terms of the Fibonacci sequence. Those are kind of fun. All right, so that's one of the ones. The ones that I'm doing this, some of it you'd have to understand, like the terminology. Now we're talking about limit superior and limit inferior of a sequence, and it's kind of. And then we're getting into more familiar stuff now, proving that a function is continuous and a function has a limit, but all going from the epsilon delta definition, and using this idea of lower bounds and upper bounds and limit superior and limit inferior. We're really starting at the foundation. So the only thing that we're assuming that we know what a function is, we know what those things are, but all we assumed was that a bounded sequence has the least upper bound. That was our axiom, and everything's following from that axiom. It's kind of interesting. All right, so let me give you some proofs that you can work on. I just wrote a few down. And I'm going to say show that. And when we say show, that means prove. Square of an even integer is even. And the examples we did should help. If m squared is odd, then m must be odd. Square root 3 square root of 3 is irrational. Sum of 2 rational numbers is rational. And then one that's related to calculus very easy proof, and it tells you, it gives you a hint, or it suggests how to go about it. Page 392, number 101, involves hyperbolic trig functions. It's a nice one. And then I have a bonus. So we know that the tangent line approximation to for f of x at a is f of x equals f of a minus f prime of a times x minus a. And we use this in Newton's method. And then I'm going to say plus some error, where this e sub f is the error. In the approximation. We want to show that the limit as x approaches a of e sub x over x minus a equals 0. And my hint here is you need to know the definition of the derivative. This one looks a little intimidating. It's really not that bad, but it's a little more calculus related. All right, there we go. Well, tomorrow we will talk about proof by induction. Induction's a really powerful method. Not that these others aren't powerful.